All right. Welcome back, everyone. So the next speaker today is Sanjeev Arora. Sanjeev really doesn't need any introduction. He's one of the giants of theoretical computer science. He's a twice recipient of a Gödel Prize, Fulkerson Prize, a member of the National Academy of Sciences. He's also one of the progenitors of the area of theory of deep learning. In the recent couple of years, he's been thinking about getting a mathematical and conceptual understanding of language models. And he's also the director of the new Princeton Language and Intelligence. And with that, let's welcome Sanjeev.
Thank you so much. Yeah, good fun to hear all the talks. And what I was struck by was that all of us are basically thinking about very similar things. And to all the previous speakers, I want to say the right topic or the right phrasing or the right way to think about it is that we're looking at LLM metacognition. You know, you talk about skills, you talk about all these other things. It's metacognition. All right. But let me start by first, maybe not in this audience, but like in a general audience, when I give this talk, like there's still people out there who say, like, what, you know, LLMs are just, you know, autocomplete, blah, blah. And, you know, stochastic parrots critique. So there's that, right? So let's just acknowledge that there are people out there who think LLMs are just basically parroting back things they are seeing from the text or so on. Then there's also the curious case of chain of thought, which is very striking when it came out, I remember. Like, yeah, you have this math question, kind of the ones people were talking about, and let's say the LLM says answer 7, which is wrong. And so then these people just, before putting, so this was still in the days when the LLM were predicting the next word. So, you know, if you make it a next word prediction, then you get 7. But if you just put answer, let's think step by step, and now do next word prediction, and then you get this. Okay? So by just prompting it, you know, let's think step by step, and now do the next word prediction, it goes into a different frame of mind, so to speak. I mean, it's controversial to call LLMs having a mind, but okay, so, and then they produce this, right? So I think everybody here has probably seen this. And again, then you wonder, and you know, there's the stochastic parrots crowd, right? Did the LLM actually think, or is it just parroting back patterns, which is what it suggests, right? Like you put this in, and it just parroted back something that's prompted by that. Okay, and then the third reason to think about these things, you know, they're just stochastic parrots, is, you know, relevance for AI alignment and safety, which again is controversial. Some people believe there's no worry there, at least for now. But there was this, Andrew Ng posted this conversation with Jeff Hinton, where exactly Jeff was raising this point. Do we agree that chatbots are beginning to understand? And then, you know, the next thing you will ask is, you know, are they exhibiting capabilities that didn't see in their training set? And that is the main question, I think, about LLMs, the OOD generalization, and whatever that means. Because the usual evaluations, I think, let's agree, are at this point completely useless because, you know, I know people were trying to create new data sets and so on, but the whole point is that it should extend from whatever you're teaching to some new settings, right? That's the goal. And so that's the interesting phenomenon that we should be studying. Okay, and the word skills was used already in several talks today. And yes, I want to harp on that again, that, you know, the LLM field 3-4 years ago was very much about knowledge. And still, you know, people who talk about, you know, memorization or copyright and so on, you know, there's like, it's still a focus on, you know, knowledge, like this piece of knowledge. And then there's skills. Skills are general purpose. So you could learn skills from this math book or that math book, and it doesn't matter. You could probably learn skills, as we do, without memorizing the math book, right? So skills is very different. And skills are more like procedures. It's a different type than knowledge. It's procedural knowledge. And these can be themselves chained together. And that is indeed what people are thinking about as OOD, that in many cases, that they are the basic skills, and then somehow for a new task, they take this menu of skills and combine them to get new capabilities. And so the point is that complicated reasoning is procedural. So whenever we are talking about skills, that's what we're really talking about. But procedures, it's not really like programming language, of course. Give me an example of a piece of text with 2 sentences that could appear in a fiction about sushi and which exhibits use of metaphor and ad hominem attack. Now, normally, you don't find such pieces of text, but you give it to GPT-4o and it gives you something reasonable. And now you think about it, what is a metaphor? It's not something you can code up in a programming language very easily. And what's an ad hominem attack? So it's procedures, but it's not programming, but it's something procedural intuitively. Okay, so this is the rest of the talk. And I should say, I forgot to say this with the opening slide. This has been a 1.5 year long collaboration with Goyal, who was at DeepMind at the time where I did my sabbatical, and he's now at Meta. And then there are many other co-authors, as you'll see. And so the order in this list is not the order of discovery. So, okay, so, and it's actually not in reverse order either. It's a random, it's some different order. So the first point is that the ability to compose many skills implies some level of originality or novelty. That you may have seen all the skills in the training set, but if you're able to compose them a lot, like 5 skills, 10 skills, then you have to, and that's mathematically clear, but I'll go through that argument again. And the second thing is, given that fact, that composing skills seems so crucial for intelligence, can it be learned? Because you'll never see, as I'll argue in a minute, it cannot be learned from examples alone. There are not enough examples. And then what are skills? What are skills? Does GPT-4 has different catalog of skills than Claude and Gemini? And my skills are different from your skills. How do we find comprehensive lists of LLM skills? And the answer will be LLM metacognition, which we'll see. And then the other point would be how to leverage metacognition. How do you see that it's useful? And there'll be a new LLM evaluation and new training methods and mapping and understanding the rapid increase in LLM capabilities. And then I'll talk about the paper that started it, Anirudh and I did at DeepMind, the theory paper, which I talked about at a similar workshop last year at Simons. And that was still an early write-up, and I think we hadn't figured out the correct way to explain it. And so hopefully I'll do a better job in 10 minutes at the end. And then conclusions. Any questions? Okay, so let's talk about this fact, that ability to compose many skills implies some originality and novelty. And also why frontier LLMs, I don't think, are stochastic parrots. Okay, so do they have capabilities that were not in the training data? It's not clear what that means. For one thing, we don't know, the leading LLMs are proprietary and we don't know their training data. So we can't just do a search in the training data for similarity. And also the set of possible capabilities is too large. How do we test this? And as I've been suggesting so far, that the answer is compositional capability. And this is meta capability. And that was from this paper with Goyal. Okay, so I'll describe compositional capability, because as I said, skills are not easy to define mathematically. So I'll do it by example. So compositional capability. And this, after I came back from DeepMind with some students at Princeton, we did this evaluation. So it's related to that example I showed about sushi. So you start with a list of N skills, N language skills, things like self-serving bias, red herring argument, spatial reasoning, etc. Why did we choose these skills? There's about 100 of them. So that, because they're all in Wikipedia. And they have an entry in Wikipedia. So every model, big and small, has studied Wikipedia at length and knows these skills. And then
those skills have quite different sizes, right?
Sizes.
Well, spatial reasoning probably has
many
principles. The
That's
size.
right. That's right. That's right.
Yeah.
Correct. Yeah. They are not the same granularity, indeed.
Right. Exactly.
Yeah. So I'll come to a second experiment later, but for now it's just this. And there are T topics, showing, doling, etc. And these topics were selected because they are sort of frequent in the normal text corpora, but not too frequent. So again, every model knows them, but they're not too frequent. And the reason for picking them not too frequent is because we want them to be not too common in the training data, even though we don't know the training data exactly. All right, so then you start with these two lists, and then using randomness, you just create a randomized challenge. Generate a short text about sewing that exhibits these 3 skills, okay? And 3 could be 4, 5, whatever, number of skills. And just like the theory predicted, the theory paper that I didn't describe but mentioned, small models are not able to combine skills too well. It tries, but doesn't do as well. The 7 TB model, 10 times bigger, does a little bit better, And GPT-4 is much more elegant and can spin its text much better and incorporate the skills. All right, so yeah, that's what we saw in that evaluation, that capability by model size was like this. And this was exactly what was predicted from our theory, that every order of magnitude change in size doubles the list of skills. By the way, we noticed that we and the grad students also struggle with 4 skills, combining 4 skills. The funny story is that, we said, okay, we're going to do this. And they said, okay, we should time ourselves. And we're going to give ourselves 2 minutes. And then we were typing each other on Slack, this is too hard. And then I said, okay, unlimited time, just time yourself. And it was like 7, 8 minutes for all of us. Okay, so that's grad students. And the GPT-4 is already better. Now, compositional capability implies that LLMs are not stochastic parrots in this limited sense, that if you have n skills and t topics, and the task is to compute random subset of k skills, there are n choose k times t possible combinations. And if k is large enough, like 5, this gets very large. And even with 100 skills. And so there's a simple probability calculation based upon these estimated frequencies that random topic plus set of k skills are unlikely to have occurred in the training corpus. Okay, so we concluded that GPT-4 is not a stochastic parrot, and as of last September, that was the only one. I think since then there have been good models. Yes.
Trying to get a formal sense of what we mean by a stochastic parrot.
Right. Just that it hasn't seen this k tuple of skills in a small piece of text on this topic.
Yeah,
and it's able to produce that.
But another interpretation, I mean, when I think of it, I think, well, I see it as they're auto-complete, and it's like, well, we're auto-complete on an enormous amount of data with nicely structured models, in which case the generalization capabilities can mean that you get this type of behavior. Right?
That is what the theory will show, yeah. So there are some people who say, yeah, of course this is obvious, and others who are surprised, yeah. And so maybe you're the ones who are not surprised.
Yeah.
Okay, that's fine, yeah.
I don't know, I'm not saying it's obvious, but I think it's like...
Good, yeah. But there's a theory which predicts this.
Which is important because there's a lot of really crazy arguments on Twitter.
Yes.
So I wonder what Bender and Kaur, who wrote the stochastic parrots paper, would say to your argument about composition. And I wonder if they would say, well, there are simpler kinds of composition, like, I don't know, interleaving words from different topics or skills that they would still think of as parroting in a kind of round robin way.
They're fine. Yeah.
Right.
I mean, they can.
Yeah. I mean, I don't exactly know.
There's never going to be. Yeah. So, and then you point to more complicated capabilities, but they're still, the examples are all compositional. So, but the theory says, like, yes, you may know the individual skills, but composition is tough. And at least according to the scaling laws, it emerges with scale.
To clarify on that, I'm interpreting what you're saying not so much as a critique of that paper, which I think is making different points. It's just the critique of the way people are using that phrase since that paper.
No, I think that paper is, it's at this point 4 years old, and it was just the wrong way to think about it.
But it made some
That's not what LLMs. I mean, nobody here thinks that.
No, but at the time, it made some very important points.
Yes.
Based on that understanding of LLM.
Okay, so the paper was not about the stochastic parrots argument anyway, right? It was about like the data and bias and all. Yeah. It has nothing to do. Yeah, I'm not addressing any of that. Yeah, just the novelty. Yes. Thank you. Yeah, that's an important point. Okay. All right. So now the question is, can small LLMs learn to compose skills? Because as I mentioned, our theory suggested that the scaling laws imply that larger LLMs will learn to compose skills much better. Can they learn to compose skills? And this, to me, was an open question. I had no way of thinking about it. And so we tried it. So we take very similar 101 named language skills from Wikipedia, but this time we tried a somewhat different thing. So we did take different types of skills and group them. I mean, that occurs in Wikipedia too. So there were these groupings, and these were the models. And the training data was text generated by GPT-4 combining K random skills in response to requests to combine K skills. From these categories, literary and rhetorical, which were the biggest categories. And then after fine-tuning on this data, so you fine-tune. Okay, sorry, this was the training data for these small models, fine-tune on it, supervised fine-tuning. Evaluate capabilities to generate text combining K prime skills from held out categories. Yes.
So how is the evaluation done? Like
GPT-4.
Oh, I see.
Yeah. And some human spot checking. Yeah. Okay. So yeah, ignore the blue numbers here. The red numbers are the one you're looking for. So these are the results of fine-tuning. So K equals 1 data, and K equals 1, 2, K 1, 2, and 1, 3. So I don't have the one for just 1, but just look at 1 and 2. So with 1 and 2, you see that there's some improvement. Look at the red numbers on K equals 3. And when you fine-tune on 1, 2, and 3, you see improvement on K equals 4. And with Mistral, it's even stronger. And Mistral even generalizes to 5, I'm sorry. So the takeaway here is that, yes, models can learn compositionality. Now, these are, of course, very artificial-looking examples, as you saw in that previous slide. So you don't find those very much in the training data. But if you give that training data, a few thousand examples, they do learn it. And it generalizes to higher K, which was not predicted by the theory. Then it's seen, it saw K equals 3, and it generalized to K equals 4 and 5, and to held out skills. Now, granted, the held out skills are still language skills, but they are different skills. Yeah, I'm not claiming anything more general than what's on this board. Whether this applies to math skills and other kinds of skills, we know a little bit, but yeah, I'm not implying anything. Any questions? Yes.
Do you have a comment on why it's very hard to generalize large things? Because I think
Nobody knows.
Okay.
Why is it hard to generalize? Nobody knows. But as I mentioned, it was pretty hard for me. Combining 4 skills was taking me 7-8 minutes.
So it's like the combination itself is very hard.
It's very hard. Yeah.
These skills are in language that's all orthogonal to each other.
No. So that could be why it generalized to held out skills, right? That somehow there's some, I mean, there are different categories, but who knows, right? What it means similarity, right? These are procedures, remember? Yes. Another question? Yes.
Yeah, you're limited to 2 sentences regardless of K.
Yes, for K equals 3, it's 2 sentences. For K equals 4, it's 3 sentences. But we didn't do K equals 4.
Yeah. Okay. Well, this might be why it's harder for increasing K.
Yes, indeed. Yeah. Yes.
So if you don't do fine tuning, what will happen?
Oh, it can't learn in context. Is that your question? Can't do like no, it doesn't learn from context. It's too hard. Yeah. Okay, LLM metacognition. So this is the phenomenon that we arrived at. And this happened because I would give this talk last year, and I gave it here too. People say, "What are these skills? Who knows what these skills are?" So, and indeed, that is a very crucial point, and that's why all the previous speakers were, in some way or the other, talking about skills. All of us are thinking about, clearly there's skills, and somehow you have to leverage skills to improve learning, clearly. And that's what everybody's struggling with. So, but what are these skills? Because we're interested in all kinds of tasks, and there's no, so like the math skills or something, they are like books which describe, right? But in general, what are skills? So we first did it in the context of mathematical problem solving, and the lead student author is Aniket Didolkar, and with these DeepMind colleagues. Okay, so metacognition is, awareness of your own thinking, and that this whole controversy about whether LLMs are actually understanding. Let's ask the same question about humans. Like, are humans aware of what they're doing? You get a question like this, and you start thinking, okay, how do I solve this? Right? You are aware that you're thinking, right? But when you write down your answer, how do we know you were thinking, right? We don't know. So, but we are able to report that. So metacognition is humans reasoning about their own thought processes, which we aren't even aware of. But when you ask us to say, how did you do that? You can start explaining it, right? You can read your own thought processes, and that's called metacognition. And this Flavel paper is considered foundational in that field, thinking about thinking. Okay, so and the motivation there is that, like for instance, reading skills. There is such a thing. Those of us who are good readers just intuitively knew it, and children who struggle with reading can be taught to read better by making them aware of those skills. So that's what metacognition can give you. All right, so now we are interested in these, and this you've seen in several talks today, GSM 8K. So these are some kinds of questions and the solutions. And can an LLM reason about what skills it needs to solve these questions? Okay. And here's alpaca data set from Tatsu, etc. Instruction following. So instruction following is how to convert the next word predicting model into an instruction following model. So there's this question answer kind of data sets. And can LLMs reason about what skills are needed by a chat agent? And with chat agent, literally you're always looking for out of distribution performance, because the few examples you'll have, when you deploy the model and 1 billion people ask it questions, it's going to be very different. So it's really all about out of distribution generalization. So what are these skills? And it's going to be the skills that let you generalize. So here's the method, simple method. Maybe somebody will improve it. And there were ideas like this in several talks today, and I was struck by that. So the first method is from a data set. So if you have an example data set, you take task examples and give them one by one to powerful LLM, and ask it to label with skills needed for each example, and give it a format. Format could be up to 3 words joined by underscore, something like that. The paper has the exact prompt. And now you get these skill labels for individual questions, and they're going to be very, very low level. Okay, very specific to that question. And so now you feed the list of all skill labels. If you have 1,000 skill labels, you might break it into 2 or 3 pieces, and you give those skill labels to the LLM and ask it to semantically cluster them. Like, which skills are similar? Okay, so we know clustering with vectors. This is semantic clustering. The LLM has some idea of what these skills are. It gave us that list. It can cluster them. That's it. Now, this is distinct from works that attempt to locate analogs of human skills and LLM activations. This is not about LLM activations, black box access. And these are not human skills. The LLM creates the skills, the names of the skills. Right? And this is, of course, impossible for proprietary models. We don't have parameter access. And the catalogs of human skills are grossly incomplete. So this is not a very good way to proceed with this study. You have to do something like this. Yes?
A quick question for skills. For model-derived skills, do we need to be aware of any hierarchy relations among those skills? Otherwise, they might just like flat, and some of them are super scales, some of them are subscales.
Yeah, so that's what the clustering step tries to do. But I agree, it's not very perfect. This is just a first cut. I completely agree with that.
So once you look at the labels assigned to the clusters, do you observe any kind of hierarchical relations or curriculum that you can derive from this process?
Yes, we observe such things, but yeah, that's all work in progress, yeah, as you would imagine. And I'm sure it's work in progress in your groups and whatever, yeah. Yes.
Aren't you assuming somehow that like the LLM can accurately sell?
Good, I'll address the validation, I'll address. Just hold the question for a minute, yes.
I relate on that. Are we assuming that humans can accurately do that as well?
No.
Okay.
No. There's no ground truth.
Okay.
Yes. There's no ground truth, just to clarify. Okay, so here's an example. Okay, so it got these questions, it produced some skills, and those were very low-level things, very specific to the question. Cluster, and you get these clusters that answers your question. There's some hierarchy, and you get these higher-level things. Okay. So now, yeah, somebody asked this question, like, do you validate this? Like, do these make sense? Are they all of the same granularity? We cannot say that. Sorry, by the way, here's the prompt. But I mean, I described it in words. Okay, so these result in fine-grained skills, and this was a skill clustering. So the prompt here is, here's a list of skills required to solve mathematical questions, and reduce the number of unique skills by grouping similar skills into categories and give a descriptive name. So then you get these categories and these clusters. And indeed, we have, these are just what that model produced. And these are skills extracted from the math data set, which was produced here at Berkeley, Hendricks et al. And math data set, it's important, has these different categories, unlike GSM-8K, geometry, number theory, pre-calculus, etc. So you get different skills. All right, so now the validation question. So names provided by LLM1 are meaningful to LLM2, even when LLM2 is much smaller. Okay, so you can extract skills from GPT-4, and they will be we find they are meaningful to like a 7B model. Okay, how do we know that? So, for example, you can give it the skill and say, give me a question that involves that skill, and it's correct. Okay, so it sort of gets the idea from the name. And this is the other way of validating that these skills are meaningful. So if you let LLM2 select in context examples by identifying the most relevant skill in the list, so you give it a list of skills and say, here's a question. Which skills does it require? So it picks one skill. You give in context examples related to that skill. And that improves accuracy by up to 5%. So that's much more than the previous speakers, 1%. So these are more high-level concepts, the skills, and you get improvements of up to 5%. Yeah, so we think that these skills are regions in the LLM's meta-knowledge. So meta-knowledge is this knowledge that arises from metacognition. And when you give it that skill tag, it's going somewhere in that region. It's yes.
In number 2, the in-context examples have chain of thought?
Yes.
Thanks.
Yeah. There was another hand. Yes.
Wait, sorry.
Oh, yes.
LLM1?
Yeah. Skill name. So LLM1 has generated skill names. And how are they meaningful? So in first example, how are they meaningful? Ask it to generate a question and see if it makes sense.
In the second part, because
these are different. The LLM2 is different from LLM1.
Yeah, but how do you come up with these examples that are related?
Oh, LLM1 is, let's say, GPT-4. It gave you, you gave it examples and it labeled them with a skill tag. So we have that list from GPT-4. Now ask Llama 7B. Here's a question, a test question, which is not in that list. which skill does it use? It identifies a skill from that list, and you give it a question related to that skill, and that. Yeah, you were asking that question earlier, so this was the validation. Yeah. Yes.
So are these like this metacognitive skills? Are they related to like induction heads? So like where did they live?
So the question is like, where do they live in the model? So obviously for GPT-4 we can't do it, but yeah, for 7B yeah, we're trying to look now. Yeah, yeah. But it's these are procedures. That's the thing, right? Yeah, but it'd be nice to see where they live. Yeah, Neil, you have it.
So, I'm not that familiar with all the different benchmarks, but I'm sort of curious. Presumably you've thought about this. What do these examples look like when you're talking about code and describing code? Are there interesting benchmarks where you could try it?
Yes, we're trying it on all kinds of things. Yes.
Yeah.
But I only want to talk about these two right now. Yeah.
Yes, it just because it feels like then the skills are really definable, or they've still got this challenge of their abstract nature.
Both. Yeah. Some you'll recognize, some might be new. Yeah. LLMs come up with their own naming of skills, and we've also done it. So coding, math, there are like books which describe skills, right? But you can do it for all kinds of random tasks, and how to tie your shoe. I don't know what, random. It'll give you some skills. Was there another question? Yeah.
So humans are somehow like notorious for coming up with post facto stories. If you ask them,
yes,
how did you solve tasks, whatever, and like you can cook up with a story afterwards.
Yes.
How do we, I guess, exclude here that somehow the LLM?
This, right? LLM2 did not know your list of skills. It was given by LLM1. It did not know the labeling of the skills and the examples. It just said, this example out of this list of skills seems to require that skill, whatever its interpretation of that tag is.
So the implication being that you need the larger one to compose, but not to recognize.
Sorry, composition we're not talking about here.
No, I know, the fact that the smaller ones don't seem to be able to compose all these skills. Is that here?
Sorry, let's set aside the composition thing. Yeah, that's a whole different thing. Yeah, which I'm not talking about here. Yeah, I'll return to the composition thing. Yes.
I don't know if you've ever run this experiment, but is it important that LLM1 is an LLM and not like a person that's carefully reasoning about the skills? Like, is there something important about the meta-ness?
That's a great question, and we haven't. That is a good question. It's just very tedious to, well, I know you guys are heroes in doing these human experiments at very large scale with 1,000 subjects or something. That's what we need to do here. Yeah.
Could the names of skills simply be kind of pointers into the text corpus on which it's trained that tell us, which pages are relevant?
Okay, let's go on. Yeah, so for exactly as I said, math, there are some like chapter titles and so on, right? The next example won't have it. Instruction following skills. So as I said, you can do this with any task. Go home, try your LLM, pick your task of choice, look at our way of extracting skills, do it with the task for a task of your choice, and you will find this. That's my prediction. Instruction following skills. So this is that thing, converting the base model, the next word predictor, into an instruction following model. And there are these two open famous data sets, one by Tatsu et al., Alpaca, and the other is UltraChat. So these are examples of skill clusters. Now these are, some of them are about knowledge, some are for like content production, skills for effective communication, etc. Okay. So now it's a non-math example. Oh, sorry, this is still a math example, which will address a little bit of your comment. Okay. So what we did, sorry, this is this paper. Lead student author is Vedant Shah. And some of these are Princeton students, like Kai Feng is in the audience. All right, yeah.
Previous list, there were some things that were
Yes.
Seemed like a little bit more
Yes.
Information classification is
Completely agree.
than like say
Completely
astronomy,
agree.
right?
Completely agree.
In clustering, is it like a single flat clustering, or did you try hierarchical clustering?
Okay, so let me clarify one thing. Like when you get these instruction following skills, you're not trying to classify all human knowledge. It's like, in this case, there were 52,000, but we only took 5,000 of those. So in instruction following, as I said, the name of the game is OOD generalization. it's not important which of those 1,000 skills they were, just so long as they were general enough. Model learns how to answer those questions and it generalizes. That's the hope with instruction following. Now, if you were trying to classify language, that would be a whole different matter, and you would need to pay attention to all of that, the granularity and the level. Okay, so this is, was there another question? So yeah, this is the AI-assisted generation, and then there's instruct skill mix for instruction tuning, which I'll get to. So first, the new math evaluation. It's called math square, and you'll see there are reasons for that math square. Okay, and so this is as follows. So math is this harder math data set. GSM-8K is grade school math. This is a hard one. Start with a list of skills extracted from math data set, about 125 or 150, something like that. You're going to take random pairs of skills to GPT-4 and Claude and ask for a question answer that combines both skills. So something like this. So indeed, yeah, Russell pointed out, you know, these are almost, these skills, the names are almost like titles of some chapter in a book, and that's fine. And if that's what it associates in its head with the skill, that's fine. That's totally fine. The name of the skill is not anything original. And then the multi-round interaction between two, so it generates this and asks for a question and answer. And then often this question and answer will be incorrect. Why? Because in math, remember, there were these very different topics, probability, number theory. And now when you try to combine random pairs of skills, you're combining skills that don't normally occur together in the training set. Or maybe they did occur, but like in some grad level math, like probability and number theory. So this random pair of skills, we think, force it to think out of distribution. Okay, and then, so you ensure that the skills were properly used. So this is the usual interaction between two powerful LLMs, could be the same LLM, to ensure that the skills were properly used and answer is correct as far as they can tell. And then finally, you need a human in the loop, because this really doesn't produce correct question and answers. This was mentioned by earlier speakers. And so, yeah, so you have to worry about that. All right, so as I mentioned, the use of random pairs of skills elicits novelty, we think. And you'll see some evidence. And then this is an agentic interaction, which is also very hot. This is just a pictorial representation. You take skill pairs, then you validate that the questions are using those skill pairs. And there's an attempted solution, and there's some interaction between models. All right, the slide you're waiting for. How good is it? So this is the new data set. Remember, the humans at the end, so they picked 1 out of 4 questions. So there were like 800 generated questions, and humans picked 200. So that's math square, math, and you see the drop. And so GPT-4 Omni, the most powerful model, is not bad, but everybody else drops a lot. And the open models drop really a lot. Yes?
I don't know what these percentages
Good.
are.
You are not supposed to know. Yeah.
Oh, okay.
Yeah. Just you see that they are, yeah. Whether they are good or bad, you don't know. It's fine.
Yeah, I don't know. If good
Don't worry about
is
it.
good or
Don't worry about it. There's going to be a slide in a second. Yeah. Any other questions? Yes. Yeah. So some of us, breathe and live and breathe all these evaluations. So we know exactly what these numbers mean. All right. So people also are curious, what's the extent of human editing? So 56% of the question answers were unchanged from the AI version. But remember, we did pick 1 out of 4, right? So we picked the best one. So there's a lot of choice there, but otherwise they were unchanged. 25% was slight rephrasing for clarity. And then the others had minor modifications, and 7% had major modifications. Okay. All right. So there are some very interesting questions. All right. So now here's a strange thing. So we were poring at this table that I showed, which you said that you couldn't make sense. We couldn't either. What is the pattern? We know some rumors, Phi is trained this way, Claude is trained this way. We're trying to see, okay, what does this give some insight into what's the best way to train LLMs? And we tried a very simple thing. Take the percentage score on math and square it, and take the percentage score on the new eval. And it's a straight line. Okay? And so the relevant things that where there's possibly signal, like these points here are anthropic models. And these points up here are GPT-4 models. So there's something different, we think, between OpenAI and Anthropic, but we don't know. But this is significant. And then it's like this. OK. So here's the intuitive explanation. Remember, we're using random pairs of scales. So if PI, so this is just a heuristic argument. This is not rigorous. But intuitively, to solve a question with two skills, you need to apply both of them correctly. So if PI is the probability of correcting using skill I, then X is this, Y is this, which is like this, which is X squared. OK? This is just a heuristic argument. This is not mathematical. So anyway, that's what we find.
Wondering how should I think really about how these two skills being used, right? Is it just it says skill, maybe it might has a kind of two kind of questions that is just about skill 1 and then another question about skill 2 kind of somehow stitched together versus actually
we cannot reel it out. So this is the whole thing about novelty, right? How novel are these? We don't know. We think they're fairly novel, like combining them. But obviously, they're not, we're not talking Terry Tao here, like this is just some, it's not that much harder. Yes.
Sorry, I think you mentioned this. Could you repeat the evaluation procedure itself for getting these results?
Evaluation, just, give it a math question and get an answer. All these questions have a single number as an answer.
Okay.
Just that's a normal business people are doing. This is not theorem proving. Yes.
Which models were used for creating the eval suite, like in the AI-assisted part?
Oh, yeah. So we used basically OpenAI and Anthropic models, a little bit of Gemini, but not much. Yes. And OpenAI models were the best, yeah.
This way, because combining two scales would be too simple. Have you tried combining three scales?
Those are very hard for models to combine. Yeah. Because compositionality is hard. Yeah.
So do the problems look like first solve this problem, then use the output of this problem to solve this other problem?
No. They don't cheat, So indeed, so you give this kind of thing, and you would say models could cheat, right? They'll come up with the obvious cheating solution. They don't seem to do that, and my explanation is that these are instruction-following models, and so they've been trained to be helpful. They're not supposed to blow you off. They make a good faith attempt. Yeah. Same with the skill mix earlier, right? Reviewers say, do they do the cheating solution? Exactly like that, like a string of unrelated sentences. They don't do that. They could, but they don't. Okay, yeah.
Maybe related to this her question. A trivial solution could be like the generated data just concatenate the two math questions.
That's exactly what he was asking, right? That could be a kind of cheating question.
But you look at the data, it's not. Okay.
Yes.
Right now, you're extracting the skills from the LLM itself. If you do just off-the-shelf clustering of the text.
What does clustering mean? No. So vector-based, no. I mean, that was a question. Like where do skills live in the activations? We don't know. So we need you can't just take an activation vector.
I'm talking about question-answer pairs.
What's a clustering? On what?
Let's say just word-to-vector representation.
No, that's what I'm saying. That's a vector. Yeah. The vector thing doesn't work. But probably once you understand where skills live, that could work. Yeah. Other questions? Yeah, word-to-vector will definitely not work. Yeah. Okay. So now next example, powerful instruction tuning. So this is, the student authors are Simran Kaur and Simon Park. So instruction tuning I mentioned, it converts base model to chat agent. And the proprietary method, which is to fine-tune the base model on instruction following examples obtained from skilled humans. And they take a lot of care and design to come up with these, tens of thousands of examples, good coverage and so on. And the open efforts were uncompetitive. Okay, maybe Tatsu should cover his ears, but there were the human queries, I think by Kuna and Dolly. I mean, For 2023, they look pretty decent, but now they really don't. And similarly for Alpaca, like these days, if you try to fine-tune models with those Alpaca UltraChat, you really don't get very good performance. And so actually an anonymous industry colleague, ran into at ICML, sort of was saying, human data is the final mode in AI. Like with Llama 3 models now out, you can get very powerful models in the open. And this colleague was saying, human data is the final mode. So then I told this colleague about this paper. And it was quite amazing. Okay, so now at least that mode maybe is following, the instruction tuning. So using metacognition ideas, what I described to you, extract list of skills from 6,000 Q&A pairs from Alpaca and UltraChat. Dataset generation, pick random pairs of skills and ask GPT-4 to generate a query answer pairs that use both skills. This is becoming old news by now in this talk. Fine-tune based models on this Q&A data set. That's supervised fine-tuning. And this actually works pretty shockingly good, and we were very happy. But it had some limitations. When you interact with it, you could see some limitations. So we tried version B of the method, so that it's not inheriting any limitations from Alpaca and UltraChat. We said, just ask the method, OK, you're an instruction following agent. Tell us instruction following skills. Give sub-skills. Just through an interaction, get a list of skills. That works actually even better. Even though this one worked better, but I think this is even better. So the benefit of random pairs of skills. So you see, suppose you have the same skill, critical thinking and communication, but then there you combine it with literature and language and this skill in virtual and system design. You get very different queries. And so, it's this random pairs of skills is promoting diversity, we think. These are very high quality questions, which you don't see in the old synthetic data sets. So here's a performance, the number you're waiting for. So the open question here was, you get these models, Llama and Mistral and Gemma, where they release the base model, the next word predictor model. And they release the instruct model. And you try to use instruction data wherever you get LMSys, LLM Playground, whatever. Alpaca, you try instruction tuning, and people were never able to match this from just supervised fine-tuning. And so here we get much better numbers than just by supervised fine-tuning with 4,000 examples. And here just 2,000 examples, which we're told is much smaller than in industry. And you get these numbers. And Wildbench is a harder evaluation. And there also our numbers are better than these two proprietary models. Gemma is the latest model, which seems a bit stronger. And these are some proprietary models. So of course, this is much, much better. But like these Llama and large Mistrals and so on are roughly in the ballpark or slightly worse. This is slightly better. So this thing actually, this evaluation has all kinds of tricky questions. So this is indeed a harder and new and hard evaluation. But still, there also we are better than the previous methods. OK, so I have a little bit of time at the end, and I'll tell you about the theory that started all of this, which Anirudh and I were working on at DeepMind last year, more than a year ago. OK, so the question was, how do these compositionality skills emerge from next word prediction? And the starting observation is that even next word prediction requires more skills. And the NLP people have known about this. So like this Vinograd example from 1970, the city councilman refused the demonstrators a permit because they feared violence. Turns out this word "they" is ambiguous, and because it could refer to the councilman or the demonstrators. And you can test that whether the model has understood that by just putting what's called the question, like multiple choice question, who feared violence? And this is called the closed question. And until 4 or 5 years ago, the models were 50-50 on such examples, the Vinograd examples. And now, of course, they ace this. OK, so now here, of course, you don't need to disambiguate. You need a question here to disambiguate. But you can easily imagine the next line involves disambiguating "they," right? And so when you train the model to reduce answer uncertainty from 50-50 to 100%, which is what it means to reduce cross entropy, it forces it to develop understanding of skills. Okay, so how is that made rigorous? So here are the hurdles. So mathematical analysis of deep learning is still in its infancy. So all the deep learning theorists, please cover your ears. But yeah, I think that's a fair statement. We're interested in new capabilities, tasks that were not seen in training. What are language corpus and skills anyway? So the theory, none of these are like things that you can reason about with existing theory. So here's the TLDR version of the theory, and I'll give you details in a second. So the key assumptions, we started with what are called LLM scaling laws, which you may know. How does the performance on next word prediction improve from scaling? And there's a structural assumption about training data. The structural assumption is the following, that the text corpus has these pieces of text, local pieces of text, and the prediction task on these pieces of text are overlapping, okay? Because the skills are common across different pieces of text. So if you think of tasks in terms of skills, like the tasks have some overlap, and I'll give an example in a second. And then the main prediction of the theory, using some random graph calculations, was that for every 10x scaling of the LLM size and data set, you'll double the number of skills it's able to combine. And that skill mix evaluation roughly verified this for language skills. Questions? Okay, so what are scaling laws? So this is a cross entropy loss, which is basically measuring how good you are at predicting the next word. And this scales like this from scaling, n number of parameters, d dataset size. And the way to think about it is this is a constant term, and this is the term that decreases from scaling. And there's a polynomial decrease. And this is reducing uncertainty. It's the KL divergence. And so that's what it's saying. You look at these numbers, and basically scaling n and d by a factor of 10, which is what you do in scaling, you get something like a 2x reduction in the excess. Rule of thumb. So why does this improve understanding? What I said earlier, that when you can reduce uncertainty, that's then you predict better. All right, so now what's the theory? So we're going to think of the text corpus as containing pieces of text with a distribution on it, arbitrary unknown distribution. And T is a piece of text. Think of it as a few hundred words or something. There are a set of basic skills which underlie these pieces of text. And these could be whatever skills, we don't care. There's a probability distribution on skills, which is unknown too. Everything is unknown. Everything is unknown in this picture, and you'll see just one thing we're assuming. Then there's a set of skills that are needed for T. So this piece of text requires some set of skills. So you think of it as a bipartite graph. And now here's our assumption. To test understanding of T, nature adds some multiple choice questions to that piece of text. And if you can answer these multiple choice questions, you understand text T. So that's mathematical definition of understanding. Okay, now the statistical task associated with the skill S is, so skill S is a node over here. Take all these edges going out of this node and select among those pieces and pick one of them and answer its multiple choice questions. And the competence on the skill S is on this success rate on this statistical task. So pick this skill, randomly choose a neighbor, and answer its questions. So that's a simple task because it uses one basic skill. Now, you can also define a task with pairs of skills. So take a pair of skills, and now you're looking at neighbors of this. And there's a distribution on those, and you're picking from there. So that's a too complex task, etc. So just to illustrate, suppose nature produced this text using 5 tuple of skills. And so now this is the overlapping things. So there are overlapping tasks because there are 5 statistical tasks corresponding to those basic skills, the 5 skills. There are 5 choose 2 statistical tasks corresponding to 2 complex skills, 5 choose 3 statistical tasks for 3 complex skills, etc. Okay, so there's tasks for individual skills, pairs of skills, tuples of skills. Okay. Now the key assumption here is what we call the mixing assumption. So nature produces k tuples of skills independently from this measure and uses an unknown process to convert it into text speeds with a probability measure. And then the closed sufficiency assumption is that the model's average error in the closed prompts is tracking the excess cross entropy. So basically, this error is reducing from scaling. The point here is that this means that this underlying graph here is random. And now I'm looking at Russell because he knows exactly what's coming next. No, okay, all right. So now maybe it'll be clearer. So the key calculation here is we want to understand as the model gets better at prediction, how does the skill competence goes up. So there are these pieces of text, and it has errors somewhere, which I've marked with X. And when you scale up the model, the errors go down, so there are fewer X's. Okay? And so now the question is, how does this improve competency on the tasks related to skills and skill tuples? And it's just a question about random bipartite graphs. Okay, and so that's why I was looking at you. So this is, and now it's completely clear, I hope, Russell, that, so you have some arbitrary set here, and these are text pieces with errors, and now there are some skills, and the competence on a skill is a fraction of its edges that do not go into Y. Competence on a pair of skills is the fraction of their edges that don't go into that, and so on. So for at least 1 minus, so the theorem is for at least 1 minus alpha fraction of skills, at most beta theta fraction of the edges go into Y. This you see, right, Russell? It's just a bipartite graph theorem, random bipartite graph. So, okay, so this is called the competence curve. And the idea is to use probabilistic method to show the above holds with high probability for all Y of size theta n1. So you get out of that calculation some kind of an emergence law for complex skills. And so this is for quadruple of skills, this is for pairs of skills, this is for one tuple of skills. And the main theorem is that if you scale up the model by 10x, according to the scaling laws, then this curve shifts down over here. And this curve shifts down over here. That's what scaling implies in this theory. Okay, I realize I went through this fast. I'm just giving you an impressionistic view of this. So I'll conclude here, future work. So our theory is fairly simple, and yeah, people asked about hierarchical skills, etc., non-IID combinations, sequence of skills instead of tuple of skills, etc. These are open questions. We define skills using statistical prediction tasks. But if you're interested in intelligence, I don't know how many people here think intelligence is just statistical, or is it something more? So I think there's something more. Parameter level understanding of skills, that was a question I think earlier. Where in the neural net are these, or in this transformer are these skills living? And it's like a procedure, so you have to find it in there. You have to develop theory for emergence of metacognition. So we started with that theory that I just described at the end, and the metacognition we discovered later. And this is some very specific kind of skill. And I don't know exactly why it emerges, or at least not in a theoretical way, some quantitative way. And finally, further implications of our theory and experimental findings for better LLM training and for alignment and safety. So those are some things we are working on. Oops, thank you.
Questions for Sanjeev? So thanks for a very interesting and thought-provoking talk. I guess the model that you're assuming without too much comment, well, I guess you commented on, is the combination of skills as a matter of having all the skills. So in order to solve a problem, you need some particular set or bag of skills, I guess set, and there's no other compositional glue that you need to put them together. So you might imagine something like a grammar that put skills together into a super skill, and then you have some interesting dependencies and whether you have these, and maybe the glue only works.
That's what.
Oh,
yeah,
I'm sorry.
that's what. Yeah. More complicated settings. Yeah.
Yeah.
And even in this simple
Do you
setting,
have
yeah.
anything to say about this at this point, or it's just
No,
something
just
you
thinking about it. I've been thinking about it. Yeah. What's a good theory there? Yeah. Yes.
Different follow-up about the theory part. So did you assume the scaling law?
Yes. We assume the scaling law.
But assume that if there happen to be a different scaling law, your theory still goes through it. It's not really relying on this.
Polynomial scaling law. Yeah. There's some other scaling law. You get a different rate. Yeah.
But what if the scaling law is a little different? Is that particular to the additivity of this? Or suppose I have another emergent life cycle model.
Okay. So just to be clear, the main math thing was this theorem, this one. So this is a kind of classical kind of theorem in random graph theory. That's why I was looking towards Russell. So for the other kinds of skills, you need some other theorem, which would be harder. The kind of I haven't seen this theorem exactly, but this kind of calculations I've seen. But those would be new kinds of calculations.
So you need the additivity of the.
Yeah, depending on what new assumptions you have. Yeah. Questions? Yes, that's it.
I guess for this theory here, you need that the skills are sort of shared, discrete, and finite across all of the examples, right? So if you have a messier contextual situation where skills are like continuous space or something, then you would be trickier.
Yeah, or even, as I said, like dependencies. So using this skill, this only composes with this skills, all of those. So then you inherit all the messiness of language and of the real world. And it's very hard to do clean theory. Yeah.
It seems like
it's worth doing.
Type system where the skills might have inheritance and
yeah, all of that you can formalize, no problems, and people do that. It's just procedural, right? What's the combinatorics of it? Yeah, and with random graphs or something. Yeah.
Jason's talk in the morning, he sort of said LLMs are very well read, but not very intelligent. And in some sense, what we're seeing here is some of them are more intelligent than us in terms of combination of skills. But then I think what's interesting is there seems to be a gap. So one might argue, okay, we're just going to, so with scaling, we could get wherever we like, but only in terms of combining more skills, and actually it's 10 times each time. So you're not.
That's not the way to do it.
So then I think there's an interesting question around intelligence. So if you're left with the ability to only combine X number of skills, and you're able to interact with the world in interesting ways, what more additional interesting things do you do?
So right.
Which becomes Jason's gap of intelligence, the bit that's sort of missing.
Yeah, by the way, okay, in all of this, let me clarify.
I can't remember exactly what you said. You said
let me again clarify here. A quick clarification. The scaling law is how people are looking at things 3 years ago. Training today is already not according to scaling law, what the scaling laws were for, and they haven't published scaling laws for new kinds of training. There's an infinite types of trainings, and yeah, so all of this is open.
I think what's interesting is that even without the combination of skills, there's some sort of sense in terms of, but there's something additional on top of this to intelligence that we might be interested in. That may or may not be there to varying attempts.
Right. So, but I'm interested in understanding it at least at some qualitative level, like what's the mathematics of that?
Yeah.
All right, let's continue this at the panel, I guess. Thanks, everybody.